Good afternoon. So the next 20 minutes should be pretty easy and straightforward. I'm going to give you an introduction about a case study and also a couple interesting scenarios. So maybe two major concepts here. One is XAI. You guys probably know, something about XAI, but we probably take a different perspective. And also the case study focusing on having a comprehensive comparison between GPU and CPU, especially on performance, cost, and ESG. Before we get started, I think we should talk about, one interesting dilemma. Like, this is like 2 months ago in London, Gartner presented this, like in 3 years, by 2027, 75% of data, especially, we're talking about data analytics products like graph database. So that's the primary domain we're using graph database for, right? Will be made redundant or useless. The marketplaces will be shut down because too few customers came to use them. So as we can see, how we can get rid of, avoid this kind of dilemma. So that's the number one question. The number two challenge is even more interesting. So I'm just putting everything here. Taking training costs, like I'm just taking the GPT training costs, like things have been, the training cost has been growing exponentially over the past, several major iterations from, $400,000 to 4.6 million. That's called exponential growth. Then GPT 400 million. So we don't see GPT-5 out anytime soon because the cost is just formidable, right? $1.7 billion. And so this is the AI entropy problem. Have you guys heard of this term? It's not a popular term. This is just talking about the cost, the energy consumption, the performance. So these are all the negative things about AI, but clearly today we're not talking about the negativities, but we are talking about, like also on the right-hand side, as you can see, infrastructure convergence. So we are seeing AI and big data converging, right, for sure, but I think a lot of business people, especially back in the States and also in Europe, talking about AI being GIGO. You guys know the term of GIGO, right? Garbage in, garbage out. But we do know it's a black box. Most of the AI today, we're so used to are pretty much black box and very expensive. While big data sharing certain, common attributes, expensive to operate, to maintain, to run, and also pretty slow. So now I think it's time to talk about XAI. Regionally stands for explainable AI. I'm not talking about Elon Musk's XAI, X.AI. We are actually talking about, I think a couple interesting attributes, like accuracy problem. How can we improve the accuracy, like for prediction, for calculation, for all kinds of things, and of depth. The ability to deeply penetrate connected data. And also white box explainability, and also velocity, speed, speed with direction. So these are the four major characteristics. Like if we are talking about a converging infrastructure, are we going to have that kind of thing? And plus, like bias, low speed, higher cost, ethical concerns, unpredictability, hallucination, those are the AI entropy, AI challenge. So how can we simplify AI? So this is my main goal for today, talking about, are we able to build something, with lower cost, the lower total cost of ownership, particularly the hardware cost, and also the energy saving, to save energy consumption by 75%, and also speed up exponentially faster. All the four characteristics, but so this is only part. My talk is pretty straightforward, pretty easy, because I don't focus on the technical details. I focus on the high-level things that we've been focusing on building embedded within our product. Like the number one thing, there are a couple of things, super node penetration, like high density graph computing, dynamic pruning. So these are the features. Basically, if you break things down, when you look at our graph database, these are the main features, and you don't really find any other product. Low latency architecture that we, especially focusing on that. If you look at Neo4j's architecture plus other, many other open source products, if they have low latency data structure architecture, they probably have a more powerful, capable, horizontally scalable architecture. And on the other hand, if you are claiming to be very horizontally scalable, you don't really have a low latency capabilities. When you have like for instance, like a single query to be able to allow running ultra deep traversal. So these two things are very difficult to come together. Horizontal scalability and the deep penetration capabilities, plus all the other things, the reverse entropy, the AI entropy problems, lower the cost. So how, this is like how we connect different features connecting to these features. How can we empower these, interesting features, and also to reverse the AI entropy problem. So and this is based on our latest paper. So we had some, benchmarking comparisons. I want to actually talk about a couple interesting, things. I think we use a CPU-centric architecture, and we found out if we fine-tune the system well enough, it is possible for x86 to be running. Let's forget about the cost first. But using the similar kind of setup, comparable setup, x86 can be 30 to 50% faster than the ARM architecture, ARM-centric architecture. Then even ARM can be exponentially, a couple of times or even 10 times faster than GPU-centric architecture. So we had some comparisons. So this is like comparing against an article published over NVIDIA's developer portal. So PageRank is a very well-known, super easy, it's considered pretty easy, pretty straightforward in terms of computational complexity, right? So PageRank, it's a pretty easy to, to tell that x86 or x86-centric architecture can be exponentially faster than NVIDIA's GPU architecture. But when we look at a more complicated, more sophisticated graph algorithm like Luwen is considered exponentially more complex, right? But I think we found the same pattern, like, x86 faster than ARM, only slightly, 30 to 50%, which is considered slightly, comparing with, exponential performance advantages over the GPU-centric architecture. But if we look, on the right-hand side, we look at it carefully. We also made comparison in terms of, the carbon footprint. So as you can see, on the bottom, right? So the ARM architecture is actually 75 to 80% greener, in terms of the reduction of the energy consumption. And also, the x86 architecture is 50% greener. But we also look at cloud cost, when everything goes cloudified, and also versus the bare metal, the standalone, not standalone, yes, the bare metal, the hardware cost. When you own it, we can see the similar kind of a reduction, by 70, maybe to 75%. But cloud in general, is actually more expensive than the bare metal setup, which is, quite interesting. And I think if we consider long-term operational cost over cloud is maybe even a couple times more expensive. But the proportion, the ratio between, the three different kind of architectures are pretty obvious. This is aligned and consistent across all kind of setup. And also in terms of speed up, very consistent, for different kind of algorithm, for PageRank, for label propagation algorithm, for PageRank, for random walking, for graph embedding, all kinds of. It's very consistent. And one of the reasons why isn't GPU, theoretically speaking, faster than CPU? Yes, it is. It could be, but I mean, like GPU is only good at matrix computation. Not everything. I mean, plus certain graph algorithm can be very difficult to make it run in parallel. So this is the key thing. Even though you may have thousands of cores, you can't really use up all these cores. So with only like 20, 30, 50, 100 cores, of the CPU, if you can truly utilize it, it is possible that you can outperform GPU. So I think that's what we, believe and prove to be true here. Now I think I can give you guys in the next maybe 10 minutes introduction about the interesting use cases, focusing on talking about accuracy, depth, white box, explainability, and velocity. So this is the real world use case. We use our graph database to help a large retail bank to do the credit card turnover or credit card spending prediction. And essentially the bank has been using, in our opinion, the traditional big data frameworks, using many servers, like 20, maybe 40 plus. We use only 3, server instances. And the number one complaint from the business department was the prediction accuracy was not good enough in terms of mismatch. The mismatch is always over 2%. So they want to lower it to 1%, ideally to around 0.5%. And it's impossible. And this number 2 complaint was that too slow. So we use graph. Remember, this is a credit card transaction naturally forming a gigantic network. And by running graph algorithm, even doing the data sampling, using graph database, the data sampling is much faster. Running the algorithm can be much faster. Remember, we're building real-time graph database. So I think our graph algorithm running way more faster, like probably 100 times faster than the previous, sampling and generating the coefficients for downstream prediction process. So that way we can lower the whole sampling, training, prediction process from 2 weeks to around like 2 hours. Remember, this is 100 times performance improvement. And because it's a naturally a network using the graph algorithm generating the coefficients, making the downstream prediction much more accurate. So we were able to help the customer, lower the mismatch very quickly within a couple weeks, just a couple weeks. So this is the second use case. Talking about depth, there are actually multiple real-world scenarios, like decision-making, attribution analysis. I'm not sure if you work with any real customers before already. So that can be very interesting. Like the use cases here are showing supply chain use case, using like, for instance, like the Sankey diagram to visualize, how things go from like the raw materials, the end product, reversely tracing all the way to the raw materials, going through all the ports, data warehouses, all those kind of things in the middle. And if anything goes wrong in the middle, what are the alternatives? Using graph database can do all of that pretty much in real time. And highly visualized, so that's the very interesting scenarios. There's another scenario, explainability. Like if you use GPT today, any kind of LLM today, asking for relationships between, for instance, like Isaac Newton and Genghis Khan, right? GPT gonna tell you nothing, and it's pretty confident. We now know this is hallucination, right? It tells you there's no direct or indirect relationship. But we do know that all the GPTs today are trained, I think one of their data sets is the Wikipedia data set, like by importing all the Wikipedia articles, doing very simple, NLP processing, ingesting that into your database, our graph database, and you can even update that data set in real time. So you simply find the shortest path between the two entities, Genghis Khan and Isaac Newton. You're gonna find, like, I'm only returning 10 shortest paths, I think it's 4 hops apart from each other. You're gonna find something like, Genghis Khan launched Mongol invasion of West Asia and Europe, and which spread it, the Black Death. These are the Wikipedia information, right? Data extracted. And the last major outbreak of the Black Death is the Great Plague of London. Isaac Newton evaded or running away from that Great Plague of London. So, this is a causality search. We're talking about causality search. This kind of search using a real-time graph database can be done. The results can be returned in real time. So that's the benefits. And plus, it's highly explainable. If you really drill down, to different kind of data points, articles, how they connect with each other. This is another use case talking about speed. So we had a comparison. This is not specifically comparing against GPU. This is actually comparing against Apache Spark. So this is a very simple graph model. Trying to tell what are the are there fraud, for this particular, like, for instance, like credit card applications or loan applications. And we can, this, like 2 applications are sharing many similarities, many common attributes. This is a major sign that meaning one of, or maybe both, applications are fraudulent. And we can prove that what takes Apache Spark to, hours to run or minutes to run can be done in genuinely real time. So, eventually I think we found out we could be 200 to 1,500 times faster than Apache Spark, even when Spark running in pure memory mode. I think one of the reasons that Spark takes a lot of time doing the data ingestion, and also Spark doesn't really have the ability to update data in real time. So this is actually a very sophisticated use case, but it can be very significant and interesting. So we had a head-to-head comparison with Oracle. This is a liquidity risk management. So we are talking about doing 2 things. One is the financial indicator calculation, for instance, like liquidity coverage ratio. The other one is doing the attribution analysis. Now, if you look at the table, the comparison matrix, you can see Oracle takes almost 4 hours to calculate the financial indicator. It took us only 2 seconds. We got data from the same data source, like the data warehouse, right? And also Oracle couldn't do attribution analysis. If you have done that before, it's very difficult for relational database to do attribution analysis. But if you have the proper, I think if you have the appropriate graph data modeling, you can do that pretty much in real time. So, and the reason that attribution analysis basically means a very sophisticated cross-table join. And we're not talking about 2 tables. We're probably talking about 10 or 20 tables. And many of those tables have, like billions rows of data. So imagine the complexity. So that's the attribution analysis. And also TCO, the total cost of ownership. Oracle took a long time, maybe multiple years, and a few dozen people working on the project, delivering, hundreds, thousands of SQL code. And so based on our experience, when you're doing that kind of thing in GQL or in graph data modeling, it can be, I would say, 95% simpler, if not 99% simpler. there are still some basic system integration work, but I think it's much simpler. So given the time restraint, I can't really expand on those interesting topics. So, but I want to summarize. I think these are the key things: the high density graph computing, essentially, and also the supernode penetration. Those are our patented technology. Really give us the advantage, like we can use smaller carbon footprint to empower next generation business intelligence, and we have been working with not just the financial institutions, enterprise, and also regulators, doing very interesting use cases, especially use cases that were considered impossible using the traditional architecture or product. Cool. All right, that's so much for today.
Any questions here? For the online participants, if you have any questions, you can just unmute yourself. Okay.
I said it's going to be easy.
Okay, thank you, Ricky.